Bien, let's look at this interesting exercise so that we practice, the concepts, that we've looked at, the concepts that we used to solve the previous exercise, so that you understand things a little bit better. Ok? Soit F et G, les sous-espaces vectoriels de R4 définis par, so we have F, which is this space, with F, which is a family of vectors that are 4 components, and and then the condition attached here is B minus 2C plus D, and G is that, so A is equal to D, and then B is equal to 2C. Bien. So you can easily verify that F and G sont des sous-espaces vectoriels de R4, because they're going to be non-empty. There's stability by addition, and then there's stability by scalar multiplication. Now at your own time, you can sort of like check that this is actually true. Okay, but you can have hopefully you have an idea of how to go about showing that they are non-empty. They have we have stability by addition and then stability by scalar multiplication. Then the first question here is saying, donnez une base de F, de G et de F inter G. On déduit que F plus G est égal à R4, like so. Bien. So the first exercise, we're supposed to give a base of F. So just like so I'm going to say this is like 1A, like so. This is 1A. So to understand what is happening here, we have to choose, to understand, to sort of like get to the final answer, we have to choose a vector in F. Okay, we choose a vector in F, look at the condition, and then see how the vector, that vector U is going to be decomposed, Okay, so we're going to say soit U, which has components A, B, C, D, like so, a vector in F. So what does it mean for this vector to be in F? Well, it means that B minus 2C plus D is equal to 0, like so. So just like we solved the previous exercise, you are free to choose, to make any of these items the subject. It's advised that you make either B or D the subject because they have a coefficient of 1. So here B is going to be equal to what? B is going to be equal to 2C minus D, like so. Then this vector U with components A, B, C, and D is going to be decomposed. Into what? It's going to be decomposed into, so the A here is going to be A, the B is going to be 2C minus D, the C is C, then the D is D, like so. So this is what we have. Okay, this is what we have so far. Right. So now here we have 3 variables. In the previous exercise, we were at this point we only had 2 variables. Okay, but here we have 3 variables. However, decomposition is also possible here. To do the decomposition, what we have to do is that we take C and D as we take C is equal to D is equal to 0. So we're going to have A and then 0, 0, like so, and then plus. In the next iteration, we take A and C. We can take A and C. We can take A is equal to C is equal to 0. And so we're going to have 0 here. Then here we're going to have minus D. Then we're going to have 0. Then we're going to have D here. And then plus. In the next iteration, we can take A is equal to D is equal to 0. And then here we're going to have 0. And then here we're going to have 2C. Then here we're going to have C. And then here we're going to have 0. So if you add A plus 0, you get A. If you add 0 minus D plus 2C, you get 2C minus D. If you say, this is 0. If you say 0 plus C, you get C. If you say 0 plus D plus 0, you get D. Okay? So here we can factor out the A. So here if we factor out the A, we're going to have 1, 0, 0, like so. If we factor out the B, if we factor out the D for the second one, we're going to have the vector 0, minus 1, 0, 1, like so. Plus, if we factor out the C here, we're going to get 0, 2, then 1, and then 0, like so. So this is our vector V1. this is our vector v2, or this is 1 here, in case you are wondering what that is. So 0, 2, and 0. Okay, this is our v3. So here we can say that f is equal to vect of v1, v2, and v3, like so. In other words, we are saying la famille v1, v2, v3 est une famille génératrice. Est une famille génératrice de quel espace? Est une famille génératrice de f. Mais est-ce que c'est une base? Well, we are supposed to talk about we're supposed to show that these three vectors are linearly independent. Okay, here it's easy to see that they are linearly independent. You can use the same trick I used in the previous exercise, or if you're not sure, you are skeptical and all that, one thing you can do here is, if you are skeptical, you can sort of like choose three scalars, alpha, beta, and gamma, and suppose that the linear combination of these three vectors v1, v2, v3 is equal to 0, and then show that alpha is equal to beta is equal to gamma, and check whether alpha is equal to beta is equal to gamma is equal to 0. Here, il est clair que v1, v2, v3 est libre, c'est donc une base de quel espace? Une base de f. So we can see that la dimension de f is going to be equal to the cardinality of the family v1, v2, v3, like so, which is going to be equal to 3. Okay, that's the dimension. Let us look at une base de G. Une base de G, on fait le même travail, but this time we choose, now I'm going to say 1b. So we're going to say soit U, a vector that has components A, B, C, D. We take it from G. So what does it mean for this vector to be in G? Well, this is a very easy situation. We are in, because here we have that A has to be equal to what? A is equal to D, and then B they are saying is equal to 2C, which is a very easy situation or interesting situation to be in. Very simple one. Okay, so A is equal to D, B is equal to 2C. Now this means that this vector that has components A, B, C, and D is going to be, so A is equal to D, so you put D here. B is equal to 2C, you put 2C. Then C, and then D, like so. And then you take C is equal to 0, so here you're going to have D, and then you're going to have 0, and then you're going to have 0, here you're going to have D. And then you take D is equal to 0, so you're going to have 0, 2C, C, 0, like so. Here you can factor out the D, so you get 1, 0, 0, 1, and then plus, you factor out the C here, you get 0, 2, 1, 0. C'est ça? Bien. So this is going to be your vector. This is going to be the vector. This is going to be your vector W1, and then this is going to be your vector W2, like so. So we can say that G is equal to what? G is equal to vect. G is equal to vect of so 1, 0, 0, 1, like so, and then 0, 2, 1, 0. Okay, so this is what we have. This is what we what? This is what we have. So, in other words, we can say that this family of vectors W1, W2 est une famille génératrice de G. So we can say la famille W1, W2 est une famille génératrice, génératrice de G. But is it libre? It's clear. Il est clair que this family of vectors is libre, so you write the same statement here. This family of vectors, that is W1, W2, est libre and then c'est donc une base de G. So the dimension of G is equal to 2. Okay, 0 2 1 0 0 2 1 0 0 2 1 0 0 2 1 0. Right. Now let's look at the bars for the intersection. The bars for the intersection. Okay. Exercice 3. We can say that 1C. So here we take soit U that has components A, B, C, D. We take it in the intersection. Or if it's in the intersection, it means two things. It means that we actually have to satisfy the condition in F and the condition in G. So what is the condition in F? What is the condition in F? Well, the condition in F is that B minus 2C plus D has to be equal to 0. And then the condition in G is that A is supposed to be equal to D and B is supposed to be equal to 2C. Okay? So if we continue, what do we find? So for A here, you put D. If you put D for A, you put D, you have minus 2C, and then plus D is equal to 0, and then A is equal to D, B is equal to 2C. Sure, you can have some meaningful simplification here. Okay? So this is going to be this is equivalent to, so D plus D, D plus D is 2D minus 2C is equal to 0, like so. And then, that is 2D minus 2C is equal to 0. And then A is equal to D, B is equal to 2C. You can factorize by the 2. You can factorize by the 2 if you want. If you can factorize by the 2, you see that the first equation is going to mean that D is equal to C. And then we have A is equal to D. And then B is equal to 2C. Okay? So maybe to make things clear for you, I can say that C is equal to D, but D is equal to A in the next line. So, but D is equal to A in the next line. So it means C is equal to A. And then here we have that D is equal to A. And then B is equal to 2C. Like so. Okay? So C is equal to D is equal to A. C is equal to D. But in this line here, we have that D is equal to A. So meaning C is equal to A. Okay? D is equal to A. B is equal to 2C. So this is going to mean that the vector that has components X, Y, Z, not X, Y, Z, but A, B, C, D. The vector that has components A, B, C, D can be decomposed in the following way. So the A here is going to be equal to, so we leave A the way it is. B is equal to 2C. Okay, B is equal to 2C. And then B is equal to 2C. And then C, we can say C is equal to C, like so. Then this is D, like so. D is equal to A. D is equal to A, like so. Okay. Right. So we can have, okay, we can write it in this way. Let me just get rid of this. So this system that we have here, we have from the first line, you get that you get D is equal to C from the first line. And then you have A is equal to D. And then you have B is equal to 2C. You have B is equal to 2C. Oh, D is equal to C, right? If D is equal to C, it means D is equal to C. A is equal to D. It means that B is equal to 2D. Like so. Means that B is equal to what? Is equal to 2D. And then here, if you want, you can say, this one you can write it as C is equal to D. Alright, so however you want to write it. So A is equal to D, I believe. Yeah, A is equal to D. So you can write everything as D, if you want. So the vector U that has components A, B, C, D can be written in the following way. So A is equal to D. So we will put D here. B is equal to what? B is equal to 2D. So we'll write 2D. C is equal to D. D is equal to D. Okay, because D is D. Okay. So you can factor out the D. So you get, if you factor out the D, you get 1, 2, 1, 1, like so. So you can see that the intersection here, you can see that here we can see that F intersection G is equal to vect of 1, 2, 1, 1, like so. Now this is only one vector. So this vector is libre. And then you can see that this family that contains only one vector. 1, 2, 1 with components 1, 2, 1, 1 est une base de F inter G, which is going to mean that the dimension of F intersection G is going to be equal to 1. Then the last question is saying, on déduit que F plus G is equal to R4. Remember that if I take the union of the basis of F and the basis of G, I'm going to get a famille génératrice of F plus G. So this is 1C, this is 1D, like so. So if I take, that is V1, V2, V3, and then if I take W1 and W2, this is going to be est une famille génératrice, est une génératrice de F plus G, like so. Then what is our goal? Let's remember our goal. The goal is to show that F, maybe before we write the goal, we can say what we mean. In other words, we are saying F plus G is equal to vect. F plus G is equal to vect of. In other words, here we are saying that F plus G is equal to vect of this family of vectors V1, V2, V3, V1, V2, V3, then W1, W2, like so. Okay. So because for F we found 3 vectors in the bars, then for G we found 2 vectors. Okay. So F plus G is equal to vect of V1, V2, V3, W1, W2, like so. Now let's look at the goal. The goal is to show that F plus G is equal to R4. Now, in linear algebra, all we have to do is to show one single inclusion, and then we look at the dimensions. We check if the dimensions are equal. Then the two spaces are going to be equal. Okay. So let's look at one inclusion. So it's clear that F plus G is included. F plus G is included in R4. Now, because if you look at all the elements of F plus G, the elements in the bars of F plus G in this family of vectors, V1, V2, V3, W1, W2, you see that they all have 4 components. A priori, they are elements of the espace R4 because they have 4 components. R4 is a space R4 is a space with vectors that have 4 components. So all the vectors, you see that they are elements of R4. So you can predict, or you can sort of like see, like the space F plus G is contained in R4. Then let's look at the dimension. So R4 has dimension. The dimension of R4 is 4. Let's look at the dimension of F plus G. Well, to be able to look at the dimension of F plus G, we have to use the formule de 4 dimensions, or the formule de Grassmann, which gives us this relation. The dimension of F plus G is the dimension of F plus the dimension of G minus the dimension of F intersection G. Or the dimension of F is 3, the dimension of G is 2, then the dimension of F intersection G is 1. So you see that the dimension of F plus G is equal to 4. So we see that we can see that the dimensions are equal, and then we've shown one inclusion. So we can say that F plus G is equal to R4. But is this family of vectors V1, V2, V3, W1, W2, is it libre in R4? Well, you can see that we have to be able to decide whether this family of vectors is libre. We look at the base of R4. You can take the base canonic as an example. The base canonic has 4 vectors. The base canonic of R4 has 4 vectors. So according to the theorem we discussed the other time, we said that if we have an espace E and we have a base of E that has n elements, then any family of vectors is going to be libre if it contains at most n elements. So here E is equal to R4. If you look at the base canonic, for example, of R4, you have 4 vectors. So any family of vectors that is going to be libre is supposed to have at most how many vectors? Here is supposed to have at most 4 vectors. Here we have 4 vectors. However, the answer here is not direct. We have to prove, we have to show, we have to consider a linear combination of these vectors. Alpha 1 multiplied by V1 plus alpha 2 multiplied by V2 plus alpha 3 multiplied by V3 plus alpha 4 multiplied by W1 plus alpha whatever multiplied by W2. We suppose that the linear combination is equal to 0. And then we verify, we check whether the scalars are all equal to 0. Okay, we check whether the scalars are equal to 0. It's different from the first case. Okay, here, even though we have 4 items, we have 4 vectors. Even though we have we actually have 5 vectors here. Sorry, we actually have 5 vectors. Because we have 5 vectors and a base of R4 has 4 vectors, this family of vectors cannot be libre. Okay, so I was counting 4 for some reason, but we have 5 vectors here. So that was a mistake. Okay. However, here we're supposed to show that f plus g is equal to R4. We've shown that. But if they ask you, is this family of vectors libre? The answer is no, because any family of vectors for a family of vectors to be libre in R4, it has to have at most 4 elements. Here we have 5 elements, or we have 5 vectors. So this family of vectors cannot be libre in R4. So that is all for this exercise. Be sure to maybe rewatch the video, go through the exercise one more time to understand what is happening here.